Math 1314, Tyler Junior College, Section 2.3, Linear Functions and Slope. In this section, we're going to discuss a specific type of function called a linear function. And you might think it's called a linear function because its graph is a line, which isn't false, but from an algebra perspective, as opposed to a geometry perspective, the word linear means highest degree is 1, or a polynomial whose highest degree is 1, or a term whose power is 1. So when we get to the part discussing linear functions, which will be a few videos down in this series, expect a function that has an x but with the highest power of 1. Before we get there, we need to discuss characteristics of lines. Specifically, one characteristic is the slope of a line. Now, several of you may have already calculated slopes of line. You may be familiar with things like slope-intercept form or y equals mx plus b, and we're going to get to all of that in a moment, but I would like to develop naturally instead of just saying, here's all the equations. So let's start with the slope of a line. On the board, I have a generic line with two generic points. Now, when we label something generically, we don't want specific values assigned to it, so we use variables. The natural variables for an ordered pair are x and y, but in order to define a unique line, I need two different points for it to go through, and I can't call them both x, y, but we can recycle those variables by subscripting them with 1s and 2s. So we could say that the first point is x1, y1, and the second point is x2, y2. So what do I mean by slope of a line? There's a lot of ways to think about slope, and if you ask most people who have had an algebra class what is slope, they'll give you a lot of things, but they'll rarely tell you what slope actually means. They'll tell you what it equals, tell you how to calculate it, but not tell you what it means. So when I talk about the slope of a line, what I'm really saying, or what I'm talking about, is a measurement that has an E there, measurement of steepness. How steep are you? So the purpose of slope is to measure how steep a line is. Now there's actually more than one way to measure the steepness of a line. A common way from a geometry perspective is to measure the angle it would make with a horizontal line. But this isn't geometry, so we're not going there. For those of you who are heading towards calculus and possibly trigonometry, you'll explore those angles a lot more in depth and make connections to slopes of lines. So how are we going to measure slope if it's not with an angle? Well, we can measure slope by forming a ratio of how far we have to travel horizontally and how far we have to travel vertically to get from one point to the next, whichever the 2 points may be. The distance we travel horizontally is called the run, and the distance we rise is called the rise. And be careful, because the word rise doesn't always mean it goes up. It's possible we could have run and then gone down and had a downward sloping line. But if we can measure the run and we can measure the rise, then the slope, whose variable is m, I know that sounds very counterintuitive. I invite you to research why slope is represented with the letter m. I'll give you a hint. It's the French's fault. So we're going to use the variable m for slope, and we're going to define slope as a ratio of how far you rise as compared to how far you run. And if you think about it, this ratio makes sense, because we would want a larger slope to indicate a steeper line. If we kept the run the same, but had a higher rise and had a point up there, then our line would be steeper, but the slope would also be greater because the numerator of the fraction would be greater. Also, we would like for a slope of a line that's increasing to be positive and decreasing to be negative. With this definition, we'll get that. If a line is increasing, then its run and its rise are both positive, or, because who's the first point and who's the second point is arbitrary, if we had gone from the second point to the first point, the run would have been negative and the rise would have been negative, and therefore the ratio would have been positive. So with this definition, an increasing line will have a positive slope, and that's good. Vice versa with a decreasing line, where if you run positive, you rise negative, and therefore their ratio is negative. Or if you went backwards, you would run negative, rise positive, and their ratio would still be negative. So this definition is nice because it does things that it should do if we're trying to measure steepness. The steeper you are, the greater your slope. If your line is increasing, we would expect a positive slope, and if your line is decreasing, we would expect a negative slope. We're just missing one important thing. How do you calculate the run and the rise? Remember, we're assuming that we're starting with two ordered pairs. Well, think about the run in terms of its x-coordinates. Specifically, if I were to project each x-coordinate down to the x-axis, x1 and x2, then the run is just how far apart these are. And to find how far apart they are, we can just subtract them. So in other words, to calculate the run, we can take the second x and subtract the first x. Using a similar argument, except projecting the points onto the y-axis, we could calculate the rise by simply subtracting the y's. Second y minus first y. Again, it's arbitrary which point you designate first and second. What's important is that you're consistent. So if you call this the first x, you better call this the first y. Or if you called this the second x, you should call this the second y. The order of the subtraction problems is actually also immaterial as long as you're consistent. Because if you were to subtract both of them in the reverse order, they would both change signs, but those two sign changes would negate each other and give you the same result at the end. So, the slope of a line is m equals y2 minus y1 over x2 minus x1. Let's just do a few examples. Give something to erase with. Formula's over there on the left, so I don't need it over here on the right. Let's say I ask you, I want you to find the slope of this line. Let's say this point over here in quadrant 2 is negative 2, 8. And let's pick this point right here, and let's say that that's about 5, 3. Just making up some numbers here. And we wanted to find the slope. First, we have to decide who's first and who's second, and the choice is completely arbitrary, but once you choose it, stick with it. Most people call the leftmost point the first point, so we'll say x1 is negative 2, y1 is 8, making x2 5, and y2 3. So let's just substitute the values. Second y is 3. First y is 8. Second x is 5. First x is negative 2. Watch your signs. In the numerator, we get 3 minus 8, which is negative 5. But in the denominator, we have 5 minus negative 2. The minus negative becomes plus a positive. 5 plus 2 is 7, and the fraction won't reduce. So our slope is negative 5/7. Slope will frequently come out to be a fraction. And honestly, we should have expected this one to be a negative slope because the line is decreasing. In the next video, we'll work a couple more examples, and we'll look at 2 special cases.